Imagine the solar system as a grand cosmic stage, where every planet, moon, and asteroid plays its unique role in a breathtaking story of creation and destruction. Here, gravitational forces shape destinies, icy moons hide oceans that may cradle life, and Saturn's rings remain one of the greatest enigmas of the cosmos. What makes the solar system so unique? How did Jupiter become Earth's guardian? Why does Uranus lie on its side? And what caused Mars to lose its atmosphere? These questions lead us on a journey to uncover the secrets of how planets formed, the forces that shaped them, and the mysteries they still hold. But perhaps most fascinating of all is the connection these stories reveal between us and the universe. If Jupiter hadn't stopped its gravitational migration, Earth might never have existed. If Saturn hadn't transported water to the inner planets, our world could have been barren. The solar system is not just our home, it's the key to understanding our past and our future. Jupiter, the largest planet in our solar system, plays a crucial role in maintaining its stability. Its immense mass, 318 times that of Earth, gives it a gravitational influence that extends far beyond its orbit. This influence is responsible for shaping the paths of countless asteroids and comets, protecting the inner planets from catastrophic collisions. One of the most famous demonstrations of Jupiter's role as a cosmic shield occurred in 1994, when comet Shoemaker-Levy 9 collided with the gas giant. The comet, which had been captured by Jupiter's gravity, broke apart into 21 fragments before slamming into the planet's thick atmosphere. The resulting explosions were equivalent to millions of megatons of TNT, leaving massive scars visible for months. This event provided scientists with a unique opportunity to study high-energy impacts in real time, reinforcing the idea that Jupiter helps shield Earth from similar fates. Beyond individual collisions, Jupiter's gravitational force also plays a long-term role in shaping the asteroid belt. It creates powerful gravitational resonances that disrupt the orbits of asteroids, preventing them from clustering in ways that could pose a danger to Earth. Without Jupiter, our planet could experience up to 10 times more asteroid impacts, significantly increasing the risk of extinction-level events. Jupiter's influence extends even further, affecting the formation of the solar system itself. Many scientists believe that in the early solar system, Jupiter's movement played a crucial role in delivering water to Earth. The gas giant's immense gravity helped redirect icy bodies toward the inner solar system, contributing to the accumulation of Earth's oceans, one of the essential ingredients for life. Another striking feature of Jupiter is the Great Red Spot, a massive storm that has been raging for over 350 years. This gigantic anticyclone is so large that it could engulf Earth entirely, with wind speeds reaching over 400 miles per hour, 640 kilometers per hour. Over the past century, the storm has been shrinking, but it remains one of the most enduring and mysterious weather phenomena in our solar system. Jupiter also possesses the most powerful magnetic field of any planet in the solar system. This magnetosphere extends millions of miles into space, creating an immense bubble that interacts with the solar wind and generates intense radiation belts. If it were visible to the naked eye, Jupiter's magnetosphere would appear larger than the full moon in our sky. With its massive size and gravitational dominance, Jupiter is more than just another planet. It is a cornerstone of our solar system structure. Its protective influence has helped create a stable environment where life on Earth could thrive. As we continue to explore this gas giant, we uncover more evidence of how it has shaped the solar system, making it one of the most fascinating objects of study in modern astronomy. Europa, one of Jupiter's largest moons, has long captivated scientists as a prime candidate in the search for extraterrestrial life within our solar system. Beneath its icy exterior lies a vast ocean of liquid water, potentially harboring conditions suitable for life. Data from missions like Galileo indicate that Europa's subsurface ocean could be up to 100 kilometers, about 62 miles deep, surpassing the combined volume of Earth's oceans. This ocean is believed to be in contact with a rocky seabed, creating the potential for hydrothermal vents. On Earth, such vents support diverse ecosystems, suggesting that similar environments on Europa could also harbor life. The gravitational pull from Jupiter induces tidal forces on Europa, generating internal heat that prevents the ocean from freezing entirely. This process may also drive geological activity, leading to surface features such as cracks and ridges. Europa's surface is among the smoothest in the solar system, with minimal elevation differences. This unusual smoothness suggests a relatively young and active surface, continually reshaped by geological processes. Observations from the Hubble Space Telescope have detected plumes of water vapor erupting up to 200 kilometers, about 124 miles above Europa's surface. These plumes offer a tantalizing glimpse into the subsurface ocean, as they may carry materials from beneath the ice. Future missions aim to study these plumes to gain insights into the moon's potential habitability. NASA's Europa Clipper mission, scheduled to arrive at Europa in 2030, aims to assess the moon's potential for supporting life. The spacecraft will conduct detailed studies of Europa's ice shell, subsurface ocean, and geological activity to determine its habitability. The combination of liquid water, essential chemical elements, and energy sources makes Europa a compelling target in the search for life beyond Earth. Hydrothermal vents on the ocean floor could provide the necessary conditions for microorganisms, similar to those found near Earth's deep-sea vents. Ongoing and future explorations of Europa will enhance our understanding of this intriguing moon and its capacity to support life. Uranus, the seventh planet from the Sun, is one of the most enigmatic and least explored planets in the solar system. Its unique characteristics and extreme conditions make it a subject of ongoing interest for astronomers and researchers. Uranus is famous for its extreme axial tilt of approximately 98 degrees. This means the planet essentially rotates on its side, which is unparalleled among the planets of the solar system. Due to this tilt, Uranus experiences extreme seasonal variations, where each pole alternates between facing the sun directly and being completely in darkness for 42 years. This results in prolonged periods of continuous daylight or night at its poles. The atmosphere of Uranus is composed primarily of hydrogen and helium, with traces of methane that give the planet its characteristic pale blue color. Uranus has the coldest atmosphere in the solar system, with minimum temperatures reaching negative 371 degrees Fahrenheit, negative 224 degrees Celsius, making it even colder than Neptune, despite being closer to the Sun. Scientists are still investigating the reasons behind these extreme temperatures. Despite these frigid conditions, winds on Uranus can reach speeds of up to 560 miles per hour, 900 kilometers per hour, generating powerful storms and atmospheric vortices. These extreme weather conditions add to the planet's mysteries. Uranus has 27 known moons, the largest being Titania, Oberon, Umbriel, Ariel, and Miranda. Interestingly, most of Uranus's moons are named after characters from the works of William Shakespeare and Alexander Pope. Additionally, Uranus is surrounded by a system of rings, though they are much fainter than Saturn's. These rings are believed to be composed of ice particles and rocky debris, possibly remnants of shattered moons or comets. One of the most peculiar features of Uranus is its asymmetrical and tilted magnetic field. Unlike most planets, Uranus's magnetic field is tilted by about 59 degrees relative to its rotational axis and is offset from the planet's center by nearly one-third of its radius. This results in a highly complex and irregular magnetosphere, which fluctuates dramatically as the planet rotates. This unusual magnetic structure causes rapid changes in Uranus's auroras and affects how the planet interacts with the solar wind, making it one of the most bizarre planetary magnetic fields in the solar system. To date, the only spacecraft to have visited Uranus is Voyager 2, which flew past the planet in 1986. It transmitted detailed images and data that greatly expanded our understanding of Uranus. Voyager 2 discovered 10 new moons, studied the planet's ring system, and provided insights into its atmospheric properties. These findings significantly enhanced our knowledge of Uranus's internal structure and climatic conditions. Future space missions may offer even deeper insights into this mysterious planet and its many unanswered questions. Saturn, the sixth planet from the Sun, is renowned for its stunning rings, making it one of the most recognizable planets in our solar system. These rings are primarily composed of ice particles and rocky debris, ranging in size from microscopic grains to several meters in diameter, with a total mass estimated at approximately 17,000 trillion tons. However, Saturn's uniqueness extends beyond its rings, encompassing various intriguing characteristics. The origin of Saturn's rings has long been a subject of scientific debate. One leading theory suggests that the rings form from the remnants of an icy moon or comet that ventured too close to Saturn. Upon crossing the Roche limit, the distance within which a celestial body's tidal forces would disintegrate an object, the satellite was torn apart by Saturn's gravitational forces, resulting in a multitude of fragments that eventually formed the rings. Another hypothesis proposes that the rings are the aftermath of a collision between two icy moons. Recent computer simulations support this idea, indicating that such a collision could scatter sufficient icy material around Saturn to create the rings observed today. In this scenario, the rocky cores of the colliding moons would not disperse as widely as their icy mantles, explaining the rings' predominantly icy composition. Determining the age of Saturn's rings has been challenging. Data from the Cassini spacecraft suggests that the rings may be relatively young, possibly forming around 100 million years ago. This conclusion is based on the ring's brightness and purity, indicating minimal contamination by cosmic dust. However, recent studies propose that the rings could be much older, potentially dating back to the early stages of the solar system, approximately 4.5 billion years ago. These studies suggest that the rings' clean appearance might result from processes that prevent the accumulation of dust and debris, allowing them to maintain a youthful look despite their ancient origin. Regardless of their age, research indicates that the rings are gradually losing mass due to gravitational interactions with Saturn and bombardment by micrometeoroids. Estimates suggest that the rings could dissipate entirely within the next 100 million years, a relatively brief period in cosmic terms. Saturn's rings exhibit a complex structure, comprising thousands of individual ringlets separated by gaps. The most prominent rings are designated as A, B, and C, with ring B being the brightest and most massive. Between rings A and B lies the Cassini division, a gap approximately 4,800 kilometers wide. The rings are primarily composed of water ice, which accounts for their bright, reflective appearance. Trace amounts of silicate minerals and organic compounds are also present, offering clues about their origin and evolution. Some particles within the rings share compositional similarities with Saturn's moons, supporting theories that the rings may have originated from a destroyed satellite. Saturn possesses a powerful magnetic field, which, while weaker than Jupiter's, still provides significant protection against solar wind for the planet and its moons. Notably, Saturn's magnetic field is almost perfectly aligned with its rotational axis, a rare characteristic among planets. The planet's atmosphere is predominantly composed of hydrogen and helium, with traces of methane, ammonia, and other gases. Saturn is known for its colossal storms, some of which can persist for years. One of the most famous is the Great White Spot, a massive storm that occurs approximately every 30 Earth years and can encircle the entire planet. The most detailed information about Saturn has been obtained through the Cassini mission, which studied the planet from 2004 to 2017. Cassini provided unprecedented data on Saturn's rings, atmosphere, magnetic field, and moons, significantly enhancing our understanding of the planet. Despite these advancements, many questions remain unanswered. Future missions aim to further investigate the rings, to determine their precise age, and to explore whether they contain remnants of an ancient moon. Continued exploration is expected to unveil more secrets of this magnificent planet and its unique ring system. Mars, known as the Red Planet, may have once been similar to Earth. Around 4 billion years ago, it had a thick atmosphere, liquid water, and possibly even oceans. However, today, it has transformed into a cold, barren desert. The loss of its atmosphere and water remains one of the greatest mysteries of planetary science. Early in its history, Mars had a magnetic field similar to Earth's, protecting its atmosphere from the harsh solar wind. However, about 4 billion years ago, this field disappeared. Scientists believe this happened because Mars' core cooled too quickly, stopping the movement of molten metal inside the planet, which is necessary to sustain a magnetic field. Without this protective shield, Mars became vulnerable to solar wind, which gradually stripped away its atmosphere and left it exposed to the vacuum of space. As the atmosphere thinned, Mars lost its ability to retain liquid water on its surface. Scientists have found evidence of ancient river valleys and dried-up lake beds, indicating that rivers once flowed across the planet and vast bodies of water existed. However, as the atmosphere disappeared, water started evaporating and breaking apart due to solar radiation. Over time, hydrogen and oxygen molecules escaped into space, leaving the planet dry. Although most of Mars' surface water was lost, recent studies suggest that large underground water reservoirs may still exist. Radar scans have detected potential liquid water beneath thick layers of ice at the planet's poles. Some models even propose that deep beneath the surface, there could be hidden subsurface lakes that remain liquid due to their high salt content. If Mars once had liquid water for extended periods, it might have also supported life. Scientists are searching for organic molecules and chemical traces that could indicate past microbial activity. NASA's Perseverance and Curiosity rovers have already confirmed the presence of organic compounds in Martian soil, though there is still no direct evidence of life. Despite its harsh environment, Mars remains one of the most promising candidates for future colonization. Scientists are exploring various survival strategies, such as constructing habitats underground to shield from radiation and using local resources, like frozen water, to generate oxygen and fuel. Mars is a planet that transitioned from a potentially habitable world to a dry, desolate landscape. By studying its past, scientists hope to answer not only questions about the history of the red planet, but also the broader possibility of life beyond Earth. Our journey through the history of the solar system has shown that no planet remains unchanged. Worlds we once thought of as stable have undergone massive transformations, shaped by gravity, cosmic collisions, atmospheric decay, and internal forces. Jupiter is more than just the largest planet. It is the architect of the solar system, its gravity shaping the orbits of other worlds. Europa reminds us that even in the coldest, darkest corners of space, life may still exist. Uranus stands as a testament to chaos, proving that a single catastrophic event can tilt an entire world. Saturn's majestic rings are proof that even the most awe-inspiring structures are temporary, and Mars serves as a warning that a once habitable planet can lose everything, leaving only traces of what once was. These 5 planets have shaped the history of the solar system, and they also offer a glimpse into its future. One day, Earth may face similar changes, but for now we are the only ones able to observe, study, and learn. The solar system is not a fixed structure. It is an ever-evolving cosmic story, and its final chapters are yet to be written. Thank you for watching. Subscribe to the channel because there are many more exciting space discoveries ahead.